All right, hello AP students. Welcome to your AP equilibrium problem walkthrough that includes actually I think two conceptuals this time, and then one AP question where we address equilibrium expression and equilibrium calculation. So again, look in the description for where the timestamp would be to skip to the straight AP question if you feel really comfortable with the conceptual. So on page 2, question number 6 in your Unit 7 workbook, what does the value of K tell you about the reaction, about how the reaction proceeds at equilibrium? So if we have a large K value, don't forget the K equilibrium, all right, is a mathematical expression that involves the ratio between the products, the concentration of products raised to their relative coefficients all over the concentration of reactants raised to their respective coefficients. And that looks like an R, so I'm going to do a little P up here. And we have various versions of K with respect to the type of reaction or chemical process that we're looking at, but this is the overall format. Okay, so a large K would indicate that quantitatively my product concentration is much higher than my reactant concentration at equilibrium. Thus, we would say that equilibrium is found at a point in the reaction where the reaction, okay, favors the product side. And thus, the reaction goes nearly to completion. If you have a small k, it's the exact opposite, right? The reaction favors reactant side. And thus, we would say the reaction basically does not go to completion, right? You could just continue on the concept. What about Q? Okay, so Q is a very similar to K. The only difference is that Q is the ratio of the products raised to their respective coefficient divided by the ratio of the reactants raised to their respective coefficient at not equilibrium. This is technically at any point or state of the reaction, whether you're in equilibrium, out of equilibrium, past, before, all of that. Q is just, okay, where are we at? When Q equals K, that tells you that we're at equilibrium. But oftentimes what we do is we actually compare when Q doesn't equal K, and we use that comparison of Q and K values, both of which have no units, in order to predict which direction the reaction will proceed in order to restore or achieve equilibrium. So if K is less than Q, the reaction, what that tells me is that at equilibrium, I have more reactant than I do currently where I am testing or analyzing or measuring my reaction. So that means that the reaction, in order to get back to that state of more denominator, more reactant concentration, the reaction will proceed or shift, okay, towards reactant. On the other hand, if your Q is less than your K, all right, that means that at equilibrium, you have actually more product than what you currently have right now. So you will notice that your reaction will proceed or shift toward products to restore or establish equilibrium. Okay, so that's the first one. Now let's go to question 8 on page 3. So this now is beginning to get into the ICE table KEQ problem calculations, where you had 3 types of scenarios that you would be asked to potentially solve, where you're just basically, you're either given KEQ and you're given 2 out of the 3 following variables, right? KEQ, concentration at a specific point, and then concentration at equilibrium, right? Between these 3 values, you can figure out a lot, okay? All right, sorry, initial concentration, KEQ, and concentration at equilibrium. What happens is depending on, we remove one of these variables, right? One of these variables, and those are the three types of sets of problems you can have. We solve these in ICE tables. ICE tables are just a fancy way of a technique that we've developed as chemists, and by we, not me, like definitely not me. And where I stands for initial, C stands for change, and stoichiometric change, right? You change according to stoichiometric molar ratio, and E stands for concentration and equilibrium. And what we have here for this problem is you are told that you have equal volumes of 1.6 molar Ag plus and 2.6 molar S2O3 minus mixed. So you are told your initial values, okay? And the Ag S2 blank at equilibrium was 0.35. Okay, so you're told your final. Complete the ICE table below and determine the KEQ. Reminder, whenever you mix aqueous solutions, there's a dilution effect. So what we have to do is we're told our initial and we're told our final equilibrium value, and we need to determine for actually final equilibrium value for only one of the reagents. And we need to determine, okay, what is our total equilibrium concentrations for each respective reagent in order to plug it into the KEQ expression. But here's the catch. We mixed two things. So we actually need to find the diluted, okay? The diluted molarity of the two initial ions. And we're told that we have equal volume. So essentially by mixing two equal volume things, the dilution effect will be having the molarity, right? Because you just doubled the volume, right? You essentially doubled the volume, so you have the molarity. Okay, so the molarity of Ag plus was originally 1.6 molar, and what we will write in is that now it is, when mixed and to react, it is 0.8 molar. Okay, and honestly, you don't need to include the molar because we're assuming here that you're already in molar, so we're just going to tack on that unit at the end. And then we were told that S2O3 minus was 2.6 molar. Now in its mixed diluted environment, it would be half that, so 1.30 molar, okay? We're in equilibrium with the production of AgS2O3, and we are told, obviously in the beginning, that we don't have anything, right? If we initially mix everything, you don't have any product. And then we're told, in addition, from the word problem, that at equilibrium, the final concentration of the product was 0.35. So from there, now we need to fill in the rest of the table. Well, I know that if I'm at 0.35, I'm going to be changing my product. The change in molarity of my product is 0.35. And then looking at my molar ratios, for every one product I produce, I consume 2 of my S2O3 minus reactant. So I'm going to say that my change is twice that, and I'm actually going to lose it. It's a negative change. So 0.70 is my change for S2O3 minus ion. And then for my Ag plus, it's a 1-to-1 ratio with my known Ag S2O3 product change. And so it's a 1-to-1 ratio of change. And again, all I do here is now flip the sign and say, well, I'm not gaining this change. It's a negative change. I'm losing this molarity. And so then when you fill out your change, you can just do basic math and solve, okay, well, 1.3 minus 0.7 is 0.60, and 0.8, and I guess I should have written 0 to keep in track with sig figs, is 0.45. So now I have the concentrations at equilibrium of my respective species. Now I take this and I plug into my KEQ. So I say KEQ is equal to the ratio of products, right? Products raises. So my product here is the concentration of Ag S2O3 at equilibrium divided by Ag plus concentration at equilibrium times S2O3 minus at equilibrium squared, because the coefficient in front is now its power. And what I get then is when I plug in all these values, I get 0.35 divided by 0.45 times 0.60 squared, and I get a KEQ value of 2.16, which to sig figs is 2.2. Okay, so there's your conceptual ICE table KEQ problem. Again, you have two other types where you are just given a different variety of the three variables of information and you solve for the unknown. And the biggest thing here is remember that you are relating change according to the stoichiometric ratios. So now let's go to the AP problem. And in the AP problem that we're addressing, we're actually going to finish out question number 2. We started it in previous AP question lectures. And now we're going to finish it out because now we have enough information to finish it out. So let's go ahead and get my thing set. So what you can do here is we were told previously, write the expression for the equilibrium constant Kpk in terms of pressure for the reaction. Here again, we notice that for the reaction, we never include the solid itself because technically the solid is actually given the value of 1. So that's why it doesn't, it's like we don't include it. You could write in the 1, but it just doesn't matter. And now you're asked for part B, calculate the number of moles of CO2, okay, initially placed in the container. So if you're like, wait, how do I use the K expression? No. So this is where you're seeing that FRQ questions drop back from previous units. So this is actually a unit 3 type of problem where you see unit 3. And here what you're going to notice is that if you need to calculate the number of moles initially, this is all initial condition. This is initial is like a static condition, right? A specific state, okay? In the container. Well, you're told initially the pressure, okay? You're told the temperature and you're told the volume. So essentially what you should actually notice is that this is a PV equals nRT question, okay? That starts with your KEQ, asks you to unit, what are we on unit 7? Jump back to unit 3, okay? In order to get a value that you will need, again, to jump to another unit, okay? So PV and RT, you have P and V, you have R because that's a constant, and you have T already given to you initially in the prompt. And so what you need to account for is I would rearrange the variables first. So it's N equals PV divided by RT. And give me a second. All right, sorry guys, the student just stopped by with their dog, and of course I had to try to win it over. It was unsuccessful though, so I'm gonna do some internal reflection later because they say dogs are their best judge of character, and so now I'm concerned. But anyway, so we're gonna continue on, and so what we're gonna do now is, given the information in the prompt, we're gonna fill this in. And so we're going to say that N equals PV. Well, the pressure we're told at the beginning, initial condition times 0 is 5 ATM. So 5.00 ATM times, we're told that the rigid container is 2 liters. Okay, all over the R value that you would be using here with the proper units are 0.0821 liters ATM all over moles Kelvin times the temp. We're told that the initial temp is total pressure of the gases in container at 1160 Kelvin, 1160 Kelvin. And I believe then all that you need to do is actually do the math. Now, I don't have a calculator on me right now, but I am going to trust that you can push a button and correctly calculate this. So I'm just going to leave it at this. Just so you know, the AP actually does give you a point for the correct actual mathematical setup, and then it gives you a point for correctly pushing in the numbers in a calculator. So just so you know. And then you should get some value, obviously, in moles of CO2. Okay, so and let me make a little note about that. This right here would be 1 point on the AP, and then this right here would be 1 point on the AP. Okay, so part C, okay, we have C, D, and E, and this is that will be the end of the AP question 2. For part C, we are told that for the reaction mixture at equilibrium, the partial pressures of CO2 is 1.63 atm. Calculate the partial pressure of CO. Okay, so what we see is that partial pressure right now, let's see, C2CO and CO, okay, and we're told that the partial pressure for CO2, let me do CO2 is 1.63 atm. Okay, now at equilibrium is a really important word here. At equilibrium. So we look back at our table, okay? How they wrote this is supposed to stimulate you to go back to the table. So we look back at our table and say, well, where's equilibrium? Okay. Equilibrium is achieved here, where we see that there is no longer a change in pressure. The overall concentration reflected in the pressures of the gas are staying constant. So we would say then at equilibrium, the pressure total at equilibrium is equal to 8.67 atm. Now, there are only two gases in the given equation or the given process we're analyzing, and it's an equilibrium. So you know that the species, despite being reactant and product on different sides of the equilibrium, are both still present in a certain amount at equilibrium. So we're told that at equilibrium, PCO2 is 1.63 atm. We also know from the original data in the prompt that the total pressure of the two reagents, chemical species that could contribute pressure is 8.67. So all you're doing here now is you're saying, well, then what is the pressure of CO, partial pressure of CO? So what you do is you set up that P total at equilibrium is 8.67, which equals PCO2 at equilibrium and PCO. So then all you have to do now is solve for PCO in the equation. And you would find that you would rearrange this to find that PCO equals 8.67 atm minus 1.63 atm. And you get that the partial pressure of PCO is 6.74 atm to the proper sig figs. Okay, and if you're like, wow, that's like really, really old. Okay, it is. This is I believe a unit 3. I think this is a unit 3 as well. It might even be all the way back to unit 2, but I'm not quite sure. So, by the way, for this question, you get 1 point, okay, earned for using the correct method. So I'm not even sure if you had to get the, oh no, sorry, it says 1 point earned for a correct answer supported by the correct method. So what they are asking you here, just so you know, is you actually had to show all of this to get the 1 point. Like you had to show your work. You couldn't just have written the answer blank. Like you couldn't have just written final answer PCO equals 6.74 atm. You would have had to show your mathematical process and your variable rearrangement. Okay, so for the part 2 of this question, it says now determine the value of the equilibrium constant in terms of pressure. So you now have your pressure at equilibrium values, your partial pressure. So now you just plug in using part A, your equilibrium expression in which is Kp equals the partial pressure of CO at equilibrium squared divided by PCO2. You plug this in and you get 6.74 squared all over 1.63, and you get a value of 27.9. Okay, and that is your final answer for this one. And for this one, you get 1 point for setup that is consistent with part A. So let's say you botched A, okay? The AP would still give you the point in CII if you went back and you used your A answer, okay? So note to self, it's 1 point for setup, okay, for setup in alignment with your part A, and then 2 point, and then another point for the answer, 1 point for answer. Okay, for the correct calculation. Okay, so D, okay. If a suitable solid catalyst were placed in the reaction vessel with the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst, justify your answer. So remember a catalyst, okay, changes, right? Catalyst, it changes the pathway, okay, by lowering activation energy. Okay, now we know that according to our notes, that KEQ, the ratio between product and reactant in the KEQ expression, is only changed, the value is only changed by temperature. So understanding that, what we would say then is that the answer is that the total pressure of the respective gases at equilibrium okay, will, let's see, will at equilibrium, I should say with the catalyst, okay, would be equal to the total pressure, okay, would be equal to the total pressure of the gases without a catalyst. Because catalysis doesn't affect the actual ratio and thus the actual end value, okay, of the respective reagents. All it does is it speeds up the process, but it doesn't change the end point of balance. Like it doesn't shift permanently the equilibrium position, okay? So without a catalyst, this is due to the fact that a catalyst does not affect, okay, equilibrium position. But would assist the reaction in reaching equilibrium quicker. Okay, so that is there. So that's your justification, and it really hinged on this premise right here, that KEQ, or the K value, can only be shifted by temperature itself. Okay, that's the only one that truly creates an off-kilter value between product and reactant concentration that develops a new ratio. Okay, so, and I don't know why this is so crooked. There you go. Okay, so this is all the application of that concept. Okay, so in another experiment involving the same reaction, a rigid 2-liter container initially containing 10 grams of carbon solid and CO and CO2, each at a partial pressure of 2 atm at 1160 Kelvin. Predict whether the partial pressures of CO2 will increase, decrease, or remain the same as the system approaches equilibrium. So here you should notice that you're given new conditions. And so what you're given, and then you're asked to predict, okay, where will it shift in order to reach equilibrium? So immediately you should think in your head, oh, this is a K versus Q problem, or Q versus K problem. Okay, now you've already solved for the same reaction, just slightly different conditions. You've already solved that K P is equal to 27.9 in part C double I. So we know already that KP is equal to 27.9. So what you need to figure out is, based on the values given in this new kind of experimental round, what is the current Q of the reaction equilibrium, and what will it do to reach the state of equilibrium, okay? So the K at equilibrium, okay? So Q for this, remember, we don't really care about solids. You don't even have to worry about this fact that you have 10 grams of carbon. Like, it doesn't really matter. It's not part of the problem in terms of part of your setup. And then you say Q is just like K is equal to the partial pressure of CO, okay? Squared divided by the partial pressure of CO2. Obviously, though, partial pressure is not at equilibrium. So you're told that each one is 2. So you're going to do 2.00 squared all over 2. And you get a value of 2.00. Well, when you compare this to KP, you see that Q is less than KP quite significantly. So what you would say is that we'll predict whether the partial pressure of CO2. Well, CO2, what we would see is that the reaction would shift, okay, toward, okay, the product, okay? Where you have, for the Q to be less than the K value at equilibrium, that means we have way more reactant than we want, and we want to produce way more product. We want to shift our reaction toward the product side so that our equilibrium position is found at a point where the reaction goes near to completion, okay? So that means we would see that we would use up more reactants, and therefore, and thus, as far as answering the question, predict whether the partial pressure of CO2 will increase or decrease, we would say that the partial pressure of CO2 would decrease as system approaches equilibrium. Okay. So 1 point, by the way, would be earned for this calculation. This is a 2-point question. 1 point would be earned here. And then 1 point would be earned for the correct justification, or actually not justification, but explanation. Just so you know, you could have also, the AP says you also could have done this or used an ICE table, where you had initial condition versus equilibrium condition determined again through your work above here. And you could have solved via that. I think actually the ICE table would be more work. Also valid. Why can't I write? But if you like those so much, then, and that's how your brain thinks, then awesome. So that's the end of question 2 and the end of this video. Good job, you guys. Bye.